All right, so I wrote equation 2 here again. And so for an alternative way here of solving this is if we noticed we had the mixture enthalpy that we were solving for, or had in this form before we broke it out into other terms. But this right here, we can get mixture enthalpy from the chart. So let's see what this can do for us, and hoping maybe as another way of solving this problem. So we're going to substitute equation 1 into equation 2 like we did before, and we're going to solve for our mass fluid of air. What we get is the mass fluid of air at state 1 times the quantity of our saturated liquid value at temperature 2 times the saturated liquid value at temperature 1, and all of that divided by we're going to get the mixture enthalpy at state 3 minus the mixture enthalpy at state 4, and we're going to also then subtract off the omega 3 minus omega 4 times the saturated liquid enthalpy at state 2. That part comes from when we substitute from equation 1. All right, so now we look here. We're going to get we can get that part from the chart. We'll see if we can get that one from the chart. We're probably too high for that one, but we'll talk about what we can do there. And omega 3 again, we can get from the chart. Omega 4 we do have to calculate. All right, so it might actually not be a faster way with this route, but I just want to show you what the possibilities are with this. All right, so from before we had 50 was the dry bulb temperature and 35 was the wet bulb temperature, so we ended up right here. And over on the right-hand side, we get 0.001 for the humidity ratio. But the big new thing we're trying to find here is if we travel that line up in here, we find the mixture enthalpy. Looks to be 11, 12, 13, so about 13 BTUs per pound of dry air. All right. So that's the mixture enthalpy at state 1, and for state 2, we were 120. Yeah, so we're going to be off the chart for state 2, but we can get those two values. For state 4, rather. For state 3, we have our 13 here for mixture enthalpy, and we have the 0.001 for the mixture humidity ratio, sorry. All right, so let's go back and see how we can solve for the rest. So coming back from our chart work, we have the values here. This is our 13 BTUs per pound, and the humidity ratio is 0.001. From before we calculated that this is 0.1303, so I'm not going to do that again. So the question is, how do we get this value here? Well, we already know omega 4, and the saturated liquid value at state 4 we have as well. And so we'll have to actually get the enthalpy of air, and we're going to get that from table A2. So if we write down here, we got... I'm going to keep this in red because I haven't actually found this value yet. So the value of air at state 4, and that's where we have 120 degrees Fahrenheit, the temperature. So we put here from A22E. We're going to have the enthalpy of air is at 580. Ranking, because that's tables in ranking. So it comes out to be 138.66 BTUs per pound. All right, so now if we plug this in here, our mixture enthalpy, HA plus omega times the saturated vapor value, all at state 4, is going to be equal to our 138.66 BTUs per pound plus 0.1303 for our humidity ratio at state 4, and multiply that times 1,113.5 BTUs per pound. And what we get for the mixture enthalpy is 283.75 BTUs per per pound. So it's looking a little sketchy already, because if we look at this, the value we have, 200 versus 13, seems like it might be off a bit. So if we finish our calculation, we'll find that our m dot of air is far off. And the reason for this is what I kind of had a slide on in the previous lecture, is that this enthalpy, the enthalpy of air from table A22E, this one is based on it being 0 at 0 degrees Rankine. Okay, the enthalpy of air used for this mixture enthalpy that we took from the chart, this enthalpy is based on it being 0 at 0 degrees Fahrenheit, which is 460 degrees Rankine. All right, so to get this value to be on the same level as this value, we need to subtract from our 283 the enthalpy from table A22, the enthalpy at 460 degrees Rankine. All right, because this one is 0, this enthalpy of the air is 0 at 0 degrees Fahrenheit. We need to basically create that out of this equation, so we need to subtract that off of here. So watch what happens when we do that. I'm going to take our HA plus omega Hg at state 4, and I'm going to subtract off the enthalpy of the air at 460 degrees Rankine. All right, so that's going to be 283.75 BTUs per pound minus, and I'm looking at the chart here right now, so I got a 460 and my enthalpy is 109.90 BTUs per pound, and that's going to end up equal 173.85 BTUs per pound. So I mean, they look relatively close, right, between these two. I mean, they're in the hundreds, kind of what I'm trying to hint at there. But this is the value you end up wanting to be using to subtract off from that 13 to get the value you want in the end. So let's just see if that works out here. So substituting those values back in, we got the mass flow rate of the air is equal to our 100,000 pounds per hour. And we have the enthalpy, saturated liquid at T2 is our 38.09 minus our 97.98, and that's in BTUs per pound, divided by our 13 BTUs per pound minus our 173.85 BTUs per pound minus 0.001 minus 0.1303 times our 38.09 BTUs per pound. And that all comes out to be 409.5, and that's in pounds per hour. So a little bit of shift there, all right, because the other case was 38,420. Here we get 410. I guess you round up a little bit. All right, so but the thing I want you to make sure you take care of here is recognizing that the difference between this value we get off the chart versus if we calculate our value using table A22, because of the different datum points that they use. So in this case, we subtracted, so we had our mixture enthalpy that we calculated here, and it was kind of messed up because of the value here. So in this case, we subtracted off to get it down to the datum point that was the same as our chart. So 0 degrees Fahrenheit for the chart. So we subtracted off the 460 to get down to this value. Likewise, we could have taken this 13 BTUs per pound and we could have added on this value, this 109.9 BTUs per pound. We could have added that on to the 13 and then subtracted off because the math will work out that when we do this difference, it comes out to give us the same value between the two. All right, so that's what I wanted to highlight here. Again, an alternative solution, maybe some more work versus the other one. Anyways, stay consistent. All chart or all calculations, try not to mix and match between the two. So if you have any questions from this, let me know. Otherwise, I hope you enjoyed it, and I'll see you in the next time.